Hello and welcome to the second day of the MIDI conference. Before we start with the scientific program, I'd like to show you the current state of virtual Mural. Okay, so as you see, it's really interesting, and actually, I must say that this exceeded my expectations. It's really creative and interesting. So, in case you haven't posted your photo or haven't added anything, I encourage you again to do so, because it's quite a nice manifestation of our creativity as our small community of the MIDI conference. Okay, we will be starting today with the machine intelligence session 2. Papers of this session focus on bibliometric analysis of AI research, focusing also on localization, and apart others also on algorithms for crowd counting. And regarding crowds, I will have a small riddle for you today instead of yesterday jokes. Excuse me. There's a saying that 2 is a company and 3 is a crowd. So the question is, what are 4 and 5? 9. Okay, so we can start with the session now. We will have 4 papers from what I remember. The chair for the session will be Łukasz Gruszka from the Warsaw University of Technology. Hello.
Hello, everyone.
Hi, can you hear me?
Yes,
great. We can hear you well. Are you? Did you have to go to the office today in Warsaw, or are you broadcasting from home?
Actually, I work in Radom, 100 kilometers from
All
Warsaw,
right.
and I study my PhD
studies
in Warsaw simultaneously.
Okay, I asked because today, at least in Warsaw, we really had a quite strong winter attack, I might say.
The same here.
Okay, so there's quite a lot of snow. Okay, so I think we can start. Łukasz, floor is yours.
Okay, hello everyone again, and for me it's a big pleasure to be your host today during this session. First of all, I will remind you some rules and the session flow. So firstly, we will have pre-recorded presentation, and during this presentation you can write your questions on the Zoom chat, and after the presentation I will open the Q&A session, and I will read all your questions aloud, and the authors will have time to answer. During this session we have 4 presentations, and after all there will be a time for breakout rooms to continue your discussions or ask direct questions to the authors. I believe that all the presentation will be very interesting for you, and enjoy. So maybe let's begin and move on to the first paper, and it will be a paper titled A Decade of Artificial Intelligence Research in the European Union, a Bibliometric Analysis. And the authors are Agata Frankowska and Bartosz Pawlik.
Good morning, everyone. Agata Frankowska, National Information Processing Institute. Today I would like to share a short presentation on the scientific achievements in the European Union countries in the field of artificial intelligence. So this is a little bit different view on the topic during the conference. The results are based on data used during our project, which we did at the Institute in 2020 and focusing on AI scientific achievements and also national policies supporting this field. So why should we look at the scientific achievements in the AI field? There is a growing consensus that artificial intelligence will become a next general purpose technology affecting different aspects of our lives, and therefore it gained a lot of attention in political debates and also in academic world. Although it is well known that the United States and China are the current leaders, the European Union has its own ambitions. And according to the recent white paper on artificial intelligence, the uptake of AI across different sectors of the economy can support Europe's technological sovereignty. So in the context of growing attention, we pose the question of how European Union member states performed in the AI research in the past decade. Regarding materials and method, we used Scopus database. It was assumed that a publication should be included in analysis if its abstract or title comprised at least one of keywords concerning artificial intelligence. Dataset was restricted to the period 2010-2019 and also to articles and conference materials only. On the basis of this, we calculated a number of indicators reflecting three dimensions, so total scientific output, scientific impact, and also international collaboration. On the basis of the indicators, cluster analysis was performed using Kami's algorithm, and it resulted in three groups. So in the first cluster, we have Germany, Italy, Spain, the United Kingdom, and France. So these are the biggest countries in the Union in terms of population. In cluster 2, we have still Western countries, 3 Nordic countries, the Benelux countries, and also Ireland and Austria. And in cluster 3, this is the biggest cluster. And here we have Central and Eastern European countries, also the Baltic states, and 4 Southern European countries, smaller and bigger ones such as Malta and Cyprus and Greece and Portugal. Next, we used principal component analysis to reduce dimensionality in the dataset and visualize it using a lower number of dimensions, so principal components. In the end, 2 principal components out of 5 were retained, what is presented in Pytorch on the slide. The variables, so bibliometric indicators, are plotted as black arrows, and the colored bubbles are the observations, so EU member states. The first principal component separates countries based primarily on citation impact indicators, but also proportions of international publications. So it can be said that publications of authors affiliated to countries whose scientific output relies heavily on foreign cooperation are characterized by greater impacts. The member states of cluster 1 and 2, which are located on the right side of y-axis, perform well on citation impact indicators, and the opposite is true for those on the left, so countries from cluster 3. When it comes to second principal component, it puts weight on the total number of publications. So member states with the largest scientific outputs in artificial intelligence are placed above the x-axis. It is also important here that while all countries in cluster 3 generally achieved low scores in impact indicators, those located in the second quadrant had relatively large research outputs. So it can be said that this cluster is quite large, but also internally differentiated. Summing up, we have shown a clear division between older and newer member states, which has endured since 2004 accession. And possible solution for this situation can be international cooperation, because as we have seen, publications in foreign cooperation had a greater impact. And thirdly, the EU position as a one entity should be seen in a broader context, one that incorporates aspirations of the United States, China, and maybe also other players who probably will join this race. Thank you very much.
Thank you very much. And are there any questions for this presentation? Okay, I have the first question by Piotr Toczyński. Why is international cooperation so impactful? Is it because it's better funded?
Thank you for this question. So regarding, so in this presentation, we were generally focused on the patterns, so we didn't look at the specific explanation of why, for example, international cooperation is so strongly related to the better impact. But generally, there is literature which says that research which is conducted in cooperation has generally a greater impact, because it can reach a broader audience. So it is. I wouldn't say that this is only the issue of funding, but also the general behavior or pattern in which, according to which, if you work in a group, it can reach greater number of participants. So I think that this is the explanation, and it is not so much related to funding.
Okay, thank you very much. Are there any other questions? I don't see any, but I have one. Actually, I'm curious because you said that US and China are current leaders compared to European Union. But could you tell me, plus minus, what is the gap between us, European Union, and the US, for example, in this area of AI?
Generally, these two entities, like US, China, and European Union, there you can meet a lot of comparisons between them because of their scale. So because there is let's say rational to compare them, and for example, when it comes to quality, so the impact of publications. The highest impact is generally recorded for the US, and comparable impact for the European Union. But in terms of output, so a number of publications, China is strongly chasing up, and even this output is going to be higher than, for example, US output. So it is happening right now. It has started several years ago, and there are also studies and probably more policy documents which say that this impact of Chinese science and also in this field is generally is increasing. So I would say that in general the quality still belongs to United States to European Union and United States, but China is also just behind them.
Okay, thank you very much. And do you have maybe some solution for Poland and for Polish researchers to to move on to this current leaders. I mean, current leaders in European Union. For example, first and second area.
This is a difficult question because I believe that there are many interventions for this, and for example, according to this short analysis, cooperation is one solution. So cooperation with researchers from Western countries, and this is the case not only for artificial intelligence, but I think for science in general. But also generally the ecosystem of innovation and for the development of artificial intelligence in Poland would be essential. So, for example, we have a Polish national strategy for artificial intelligence development. There are some efforts to support science and higher education sector in this field. For example, we have some plans to create doctoral schools and also increase funding. So I would say that these are also some important aspects.
Okay, nice. Thank you very much. Okay, if there is any more questions, I will move on to the second presentation, and it will be paper localization using deep lab in document images taken by smartphones, and the author is Shima Baniadam Dizaj.
This is Shima Baniadam, and we want to talk about localization using deep lab in document images taken by a smartphone. First, we talk about the advantages of this work. Document digitalization is very important because with that we can reduce number of archived papers. Also, we can simplify sharing and reading and manipulating after digitalization. Also, we can keep the papers, digitalized documents longer, and we can convert the formats and use OCR on that, and the document can be always accessible. The challenges that we have in this task, one of the challenges is non-uniform lights and spots, like this image, 3D distortion and blurring, covered corners. It can be one corner or other corners too. Complex content like having table in the picture, and also similar background and content. Like this picture that you can see, the background and the paper are so close to each other. There are different data sets in this task. We use 4 of them that have more simple samples for training our neural network, and we used the most difficult one for testing our document. The algorithm, there are different algorithms and methods that were used in this task. Some of them are using additional hardware, like having extra devices, like having a case to avoid light spots, or also have a sensor to help the person that is taking the picture to take a better picture. And some of other methods are in machine vision, like corner detection, edge detection, line detection, and some of them are machine learning that are mostly use CNN, and one of them is using AlexNet. The methodology that we use is that we first preprocess our data set. We need a train set and test set. Train set and test set, and after that we would increase the amount of trained data. We used data augmentation. Data augmentation that we use are random scaling from 0.5 to 2, and random left to right scaling, or actual flipping, and randomly rotating the picture. After creating all of our data set, we divided that to train set and test set, and after that we need grand tours. To use that data set in this task, we use 2 different methods of grand tours. One of them is for evaluation, and one of them is for learning. As the picture that you can see here, there is a masked picture for this picture, that the part of paper is white and the part of the image is black. Also, we used another way to have a grant tools. We used corners position, x and y of any position. The methodology that is our main methodology is deep lab. Deep lab is like this image. It has the input image, and after that there is different part of neural networks that are connected to each other, and finally have an answer and detect the location of the paper of the document in the image. One of the parts is semantic segmentation prediction. For this task, we used MobileNet version 2. In DeepLab version 3, we can use different neural networks for this part, and we used MobileNet version 2 because we wanted to use the final results and final weights of the neural network to run the algorithm on mobile phones and devices that have simpler hardware and hardware. Another part of the neural network is for edge detection. The result of edge detection you can see here, and after that we have domain transform. Domain transform part have the result of the edge detection and semantic segmentation part, and it goes on the picture in different sites and find the pixels that are close to border of the image. The results you can see here in this image for simple images that are very easy to human eye to detect the corner. You can see that the result is completely right, and for medium images or medium images that are a little difficult for neural network, we have 74%, and for difficult one we have 58%, and in average we have 77% percentage accuracy. You can see here that on the same test dataset, the previous existed algorithms has these results, and our proposed method have a better accuracy among them. For conclusion, we introduced a new application of DeepLab for document localization, and DeepLab is not a neural network for this type of task. The final result of our proposed method has 100% accuracy, and on actually simple images, and on average it is 77%. And in the future works, we will consider geometrical features of the text and content to improve the accuracy, and most of the problem of the result is in this part of the documents, and the main improvement is on images that have lighter spots. Thank you for your time.
Okay, thank you very much. And are there any questions to the author? Okay, I see one, and there is a question about if could you kindly elaborate more about the data set you used?
Thank you for your question. Yes, of course. Actually, the data set that we used for tests, it was a data set that we collected that before, and we published a paper on that. So it has different challenges that I described on, I think, the second page of the presentation. It has different challenges and the data sets that we used for learning our neural network are the data sets that one of them is on just ID cards and other one are on A4 papers and in the different situation, different backgrounds and different paper colors and yes, if you have any specific question about that, I will be happy to answer you.
Okay, thank you very much. I hope that your answer is satisfying for the person who asked that. And I have another question,
Okay.
because I'm curious, what is the criteria in this validation process that define what picture is difficult or easy?
Okay, actually, yes, we categorize the images based on the human detection. I mean that human's eye, how can find the paper in that image and how many challenges in that image exist. Like if we have just one challenge or just simple challenges like a light spot, it is actually the simplest challenge in the image for neural network. If we have that, or if we have a few challenges in that image, so it is a simple image. But if we have different challenges in an image, so it will be in a difficult part. And that, yeah.
Okay. Okay, thank you very much. And could you tell me what is the time of evaluation this answer for the algorithm, for example, for simple sample?
Time, you mean?
Yeah, time to evaluate the sample image.
Okay, for testing, you mean? Yes.
Yes.
Maybe. Okay. Actually, it is less than a second.
Mm-hmm.
Yes.
Okay, so it's instantly.
Yes, instantly. Yes.
Okay, so do you have maybe any ideas to commercialize this solution?
Actually, it's not completely solved because we have problems on 3D distortion images, images that have 3D distortion on that. So we want to work on that before we want to commercialize the idea. Yes.
Yeah, okay.
So it will improve the result.
Okay, nice. Thank you very much for your presentation and all the answers.
Thank you for your time.
And if there is no more question, I will move on to the next presentation. And it will be the paper prepared by Said Zishan Rizvi, Mohammed Umar Farouk, and Rana Hamad Raza. And there will be paper named Performance Comparison of Deep Residual Networks-Based Super Resolution Algorithms using Thermal Images, case study of crowd counting.
Greetings and welcome to the presentation for the publication titled as Performance Comparison of Deep Residual Networks-Based Super Resolution Algorithms Using Thermal Images, Case Study of Crowd Counting. Here is a brief introduction of the three authors of this paper. Normal human perception is limited to visible light spectrum only. Conventional cameras use the same visible light spectrum to replicate human vision. However, these cameras are affected by poor weather and low illumination conditions. Beyond the visible spectrum is the infrared region, which cannot be seen by humans. Fortunately, with advancements in infrared and thermal imaging technologies, humans have extended their range of vision. The advanced thermal cameras enable vision in scenarios such as low illumination or extreme weather conditions. But their spatial resolutions are low, which can be increased by use of high-end cameras. However, it comes at a high cost, due to which alternatives such as super resolution techniques are explored. SR is an image processing technique that is used to predict and fill details in low resolution images such that the output gives an image of a higher resolution. The resolution of the input image is increased based on the scaling factor used for super resolving the image, such as into 2, into 3, or into 4. SR has major utility in areas where attention to detail is of high importance. Some of these areas include forensic analysis of surveillance feeds, person or vehicle identification, and medical imagery. A recent research trend is being noticed in SR applications, particularly using thermal images. Hence, the main contributions of this paper are highlighted as follows. Number 1, a detailed comparative analysis of 3 most popular residual networks-based architectures, EDSR, ARCAN, and RDN, for thermal images SR to analyze crowd with inexpensive training dynamics was performed. The crowd counting is performed on both sparse and highly dense static and dynamic nature crowd, with added complexities due to far-field camera viewing angles. Number 2, a suitable application-specific dataset was selected with fixed camera views for thermal images SR analysis in crowd counting applications. The sub-dataset is carefully selected to include both near and far-field sparse and highly dense crowds for better visualization and understanding. 3 different deep learning-based SR algorithms, EDSR, ARCAN, and RDN, were used in this study for comparative analysis. All algorithms are built on residual networks-based architectures. ResNets are a special case of convolution neural networks where small modifications such as addition of skip connections enable training of larger networks with improved accuracy. The figure below represents a ResNet architecture with the skip connections. A brief overview of all SR algorithms used in this research is as follows. Enhanced Deep Super Resolution Network, abbreviated as EDSR. This network is inspired from SR ResNet, which was the first ever ResNet used for image SR. EDSR removed batch normalization layer from SR ResNet, which improved overall results. Residual Channel Attention Network, abbreviated as RCAN. It uses residual and residual network, which allows training of very deep CNNs for image SR with major performance improvements. Residual Dense Network, abbreviated as RDN. This network introduced residual dense blocks, which extract local features using dense convolutional layers. Thermal images used in the study were extracted from 2 sequences of BUTIV dataset, namely Marathon 2 and Marathon 4. Both video sequences provided a good view of cameras fixed at an elevated platform to address the problem of crowd counting. Both sequences have a far-field view, which adds complexities in crowd estimation process. Videos are selected to include both sparse and highly dense crowd environments with static and dynamic motion features in multiple directions. The figure below represents the camera views obtained from Marathon 2 and Marathon 4. A total of 3,555 frames were extracted from the video sequences and then reshaped into 512 by 256 resolution to form ground truth images. All images were randomly shuffled to improve model generalization. Further, images were split into train, validation, and test sets with ratios of 80, 10, 10. For finalization of training data, ground truth images were downsampled 2 and 4 times into images with 256 into 128 and 128 into 64 resolutions, respectively. The figure below represents this conversion. Training was done using Pytorch framework on NVIDIA's GeForce GTX 1080 Ti. All networks were trained using L1 loss function with 16 residual blocks and 64 feature maps for fair comparison. PSNR metric was used during validation stage. Training was continued until loss reached numerical values of 1.5 and 3.0 for into 2 and into 4 upscaling factors. These threshold numerical values were selected based on the observation that loss graphs had started to plateau around these. Loss and PSNR graphs obtained during training for into 2 upscaling are presented below. L1 loss for RCAN reached threshold value in least epochs, that is 72. RDN took 94 epochs to reach the value, whereas EDSR had to be early stopped at 199 epochs as the graph had plateaued. Loss and PSNR graphs obtained during training for into 4 upscaling are presented below. L1 loss for RDN was able to reach threshold value in only 51 epochs. For RCAN, it took 54 epochs. L1 loss of EDSR started to plateau in this case as well, which is why training was early stopped at 300 epochs. Weights obtained during training were used to perform tests on 355 unseen images. Reasonable scores are achieved even when maximum training epochs were only 300. The metrics used to compare SR results with ground truth images were PSNR, SSIM, and LPIPS. An SSIM score close to 1, LPIPS score close to 0, and a high PSNR value represents images with a high level of structural similarity and near to being highly identical. The table below represents a quantitative comparison of selected SR algorithms on test data with into 2 and into 4 upscaling factors in terms of PSNR, SSIM, and LPIPS metrics. Based on evaluation metrics, all algorithms have accurately predicted static features in the video frames. For example, the parked cars and road. Slight difference of scores in results is because of dynamic features. For example, moving cars and pedestrians. The figure on the right represents the visual comparison of into 2 SR results, whereas the figure on the bottom left presents the visual comparison of into 4 SR results. Crowd estimation was obtained using focal inverse distance transform maps, abbreviated as FIDT maps. Pre-trained weights of FIDT maps were used to establish ground truth for crowd count. Similarly, the same weights were used for crowd counting estimation on all super-resolved images. The mean absolute error and root mean square error scores were used to evaluate the performance of crowd count. It can be seen that RCAN performed better than all other approaches using both into 2 and into 4 upscaling factors. The table below presents a performance evaluation of the obtained crowd counting results with bicubic upsampling and super resolution algorithms. This figure represents a performance evaluation of obtained crowd counting results with bicubic upsampling and selected SR algorithms. As a conclusion, all selected SR algorithms, that is, EDSR, RCAN, and RDN, generated satisfactory results, with RCAN yielding the best results for application of crowd counting. Common metrics such as PSNR, SSIM, and LPIT scores were used to evaluate the performance of each algorithm. As a future work, similar analysis can be performed with generative adversarial networks. Furthermore, a completely new architecture can also be designed. Similarly, different multi-image SR methods can also be explored for performance comparison with single-image SR algorithms. Thank you for your time.
Thank you very much. Very interesting presentation. And there are any questions for the authors? Okay, I can see any. So maybe I will ask you a question. Do you think the thermal images can be used, for example, in autonomous car, or actually maybe it is used in there? Because I know that there is a problem for the AI in this autonomous car with the difficult weather. For example, it's in very very rainy day. It's very difficult to, for example, to see the person on the road for the car, and maybe this solution you present for the super resolution in the thermal images maybe very helpful in this area. Maybe it's actually works in this, but I don't know. Do you have any information about this area?
Yeah, hi everyone, first of all.
Hello.
So thermal images is an interesting research area, and likewise autonomous vehicles as well. But you see, the problem with thermal images is that to obtain thermal images, you will have to use thermal cameras. So if we go towards using thermal cameras in let's say autonomous vehicles, it will considerably increase the prices of the whole autonomous system which is being used in those cars. It will be a good progress, I would say, in terms of autonomous vehicles. But again, we will have to compromise on the cost of those vehicles then.
Okay, that's the point. But what do you think about the validation time in these algorithms? Do you made a research to compare the time for all these algorithms you show us?
Yeah, the validation time is presented in the paper. We did calculations over that as well. It was presented in the presentation as well.
Okay, sorry.
The validation time, actually the testing time, basically, the testing time, testing was done on 355 images, and the time was noted for each algorithm to give the results on those 355 images. So our results showed that the average time on or the test for the test to run on all 355 images was it was under 1 minute. EDSR was the algorithm that was very quick to perform. It gave the results in about 10 to 11 seconds, but for all those 355 images. And the RCAN algorithm, I think it was able to give the results in around 40 to 45 seconds. However, the
Mhm.
RDN algorithm gave results in around 50 to 55 seconds for all those 355 images. So the differences in these huge differences in the time, I would say, were because of the architecture which each algorithm follows. Since EDSR is made up of a simpler architecture, the time it took to run the test on all 355 images was considerably lower than the time it took for RCAN or RDN.
Yeah, of course. Okay, I got it. Thank you very much for this answer. And maybe one of you have a question for the author. Okay, I see one question. Do you think thermal images can perform better in other computer vision problems area?
This is a good question, but I think it depends on the application. It varies from application to application basis. For example, in areas where the color is important for the images, for example, I think in object detection, the color is very important for different types of objects. So the thermal images might not perform that well in those areas. But if we if we are moving towards let's say a surveillance environment in which we have to there is a high security area and we have to detect a movement there, just a movement where the color is not of any importance over there. We just have to detect any movement that is being done in that area. So that is an application area where thermal images will perform much better than normal RGB images. So yeah, it depends from application to application basis.
Okay, thank you very much. And there is other very interesting question. Why did you use Pytorch instead of TensorFlow?
Okay. So I think this is a whole debate amongst the computer vision researchers whether we go towards the PyTorch backend or the TensorFlow. I personally prefer the PyTorch backend, but you can maybe go with TensorFlow as well. I prefer PyTorch since the ease that it takes for to set up the machine on that framework. It's a whole complicated process with TensorFlow. That is what I personally believe. Again, you can disagree, but I personally chose PyTorch because of the ease it took me to implement the algorithms.
Okay, thank you very much. If there are any other questions to the author, I think you will ask them on the breakout room. So it may be very interesting discussion. And now we are going to the final presentation on this session, and it will be normalization and bias in time series data made by Aishwarya Asesh. I hope I pronounce it well. If not, sorry. So enjoy.
Welcome to the presentation. This research is about normalization and bias in time series data, and we'll talk through some interesting facts about why normalization plays a crucial role whenever we do some data science things on time series data. And let's just see what's the proposal for the research. So data normalization is an important pre-processing step in data mining and machine learning technique, and finding an acceptable approach to deal with time series normalization, on the other hand, is not an easy step. So this is because most standard normalization processes rely on assumptions that aren't true for the vast majority of time series. There can't be any generic path which we just need to follow. And the first is that all time series are stationary, which means that their statistical characteristics such as mean, standard deviation do not vary over time. And the time series volatility is assumed to be uniform in the second assumption, and these concerns are not addressed by any of the approaches currently. And like this research provides theoretical and experimental evidence that normalizing time series data can prove to be of utmost value by trimming non-necessary data points and achieving minimum information loss by introducing a new concept called minimal time series representation, MTSR. So what's the methodology? With the aid of raw, unprocessed and non-normalized data like the UCR dataset, this research will focus on normalization techniques and understanding the influence of normalization approaches on classifier and regressor accuracy. So what we are trying to do is we are just trying to focus on like maybe just gathering 15 data points from a time series instead of thousands of them, and see what kind of value they bring to the like algorithm which we are trying to apply. And that will like reduce a whole lot of things like computation cost. It will like help us in the storage cost and efficiency of the algorithm being run. There are like various benefits over there, because considering millions and millions of time series are run in industrial academia like every day, so this is like a groundbreaker for all of them. Continuing with the methodology, like normalization methods are recognized to have like a significant impact on classification accuracy in multivariate datasets, and when data from two distributions with vastly different means and variation exist, normalization becomes critical in guaranteeing that each variation does not bias prediction. This may be less essential in univariate datasets, but despite this, the multidimensional issue space becomes simpler to train, like in a variety of predictive models, including neural networks, like as I said earlier, maybe support vector classifiers, and a number of mathematical functions rely on normalized data. Basically, like the choice of activation function in neural network is greatly influenced by this fact, and with sigmoid activations becoming essentially like very useful, like the hyperplane used in the class separation can be fitted most precisely, and support vector machines will require a standardized problem space. So while this is a more complicated topic in overall, but the research will like concentrate on time series length standardization. Experiments like scalar normalization and time series length normalization are done, and let's just jump in and discuss some of the results that we saw. So it can be observed that there is a like minimum information loss in the instance of cricket dataset, like as a time series length close to the beginning values of time series like 1200. So while this reduces information loss, one can obtain the same classification accuracy with a time series length of 40 and a slightly greater accuracy with maybe a time series length of 90. You can observe that like clearly here that when time series like length is 40, we are just capturing 90% of the distribution, and when we go a bit further, like maybe 90 time series thing, then we are just capturing a whole lot, and it doesn't make a difference if we go further up to like 1200. This is a very interesting observation and like can bring great value. One other thing that we observed was like similar results are observed for wafer datasets. So as illustrated in the figure, you can see here where the classification accuracy stays steady as the time series length increases. One can detect a clear maximum classification accuracy for a length of 30 in this dataset, and with a length of 10 or 20, a similar accuracy can be achieved as with a length of like 300. So if you use a 300 like data points time series, then it will take like, if like you're using O(n) square, then it will take like 10 times of what you can achieve with just 30 data points. So suppose like you are taking 3 hours for running a neural net, it will just reduce the whole time consumption to just maybe 30 minutes or 40 minutes, which is a great deal, because with the like growing world, the data, as everyone knows, like data is the new gold, and like things are getting really complex. But if we have such kind of algorithms, it will greatly reduce the storage cost, the efficiency, the model run time, and other aspects. Just summarizing like observation here, I just like tried it on different data sets like cricket, gestures, and wafer, and like we just see that the average accuracy and optimal length are greatly influenced, and it doesn't make sense to go with the whole time series data in most of the cases. Just discussing more on conclusion and future work. So while acknowledged to be less accurate than DTW in time series classification, like Euclidean distance measures have shown to be more stable than DTW. And in comparison, like DTW has a time series length that is optimal for highest classification accuracy. But like the findings are limited to the dataset mentioned, and we can also see that while results about the time series length and normalization approaches applies to various datasets, the nature of data always matters when it comes to like classification accuracy. So it cannot be a generic rule to reduce the dataset to a particular length. We obviously need to go through what like things are we trying to achieve, what kind of algorithms are we trying to run. And in addition, like additional research is needed to determine if the impact of time series length normalization and scalar normalization on data from the UCR time series classification archive and other sources. And also like more research on multivariate time series is a way forward from here. The information loss associated with the reduction in time series length has an impact on classification accuracy, but as addressed in this paper, like both positively and negatively. More study is needed, maybe to develop complex models for determining the smallest time series with the least amount of information loss, and this can be really helpful in like getting towards a better world with like machine learning techniques growing every day. And obviously like we are like in like the findings are limited to the data sets mentioned, but like it can be somewhat generic because we have used like cricket, wafer, and those datasets are mostly capturing all the details from the outside world, like whether it be industry, academia. So it really helps to go forward with some of the research results that we get here. And the minimal time series representation like MTSR is a great way forward, and let's like thank you for your time.
Thank you very much. And again, there is a time to ask your questions, so write it on the chat, please. Okay, I can't see any. So maybe I will ask my question, and I will ask you to take a part of the discussion from the previous presentation. And what is your preferred tool you use in this neural networks area or machine learning in general? Could you tell me?
Yeah, surely. So that's a nice question. And like, I would just like to start by saying like, this is a comparative study in which like we use like the UCR time series classification archive. And like, so we get the raw data for it. And then we try to compare it with like the new normalized and reduced like a shorter time series data, which we are calling as a minimum time series like representation. So it's like mostly a comparison between what results we get from the whole time series, which was like the normal time series, and the reduced one, which is like a newer one. And like we are using a variety of approaches here. So like the nearest neighbor classifier, like we are using the nearest neighbor Euclidean distance, and this is an error produced by utilizing one like nearest neighbor algorithm with a Euclidean distance measure, and like the second one is like nearest neighbor DTW. So DTW basically stands for like dynamic time wrapping, and in that we are using the best time wrapping window. So in this classification technique, like the wrapping window is a hyperparameter that has been computed for each data set and coupled with like error attained with this like ideal window. And like the last one is like the nearest neighbor with like a 5-step like DTW approach. And here like no time wrapping is used. So when the nearest neighbor dynamic time wrapping like classifier has no wrapping window, so this error occurs. So we are just trying to like formulate and see that like what amount of time series data is ideal, because like in most of the researches today, like maybe multivariate time series testing and other stuff, like people use thousands and thousands of data points inside the time series, and this like research basically tries to show that if you can just use a part of it and get the same results, then why to waste like storage space, computation space, and even like some of the neural net engines won't be able to run like if you have like a very exhausting time series like length. And like yeah, while there are alternative approaches here, but they may yield more accurate classifications, but like using a shorter time series will yield you like a result very close to that. And we are like mostly using Python for all the testing.
Okay, okay, I got it. Thank you very much for this this answer. But could you tell me what libraries from Python you use?
So
Yes,
we have
or
used
are you produce your own algorithms?
like we are using some of the things from scratch, and apart from that, like we are using pandas like Python framework, and also some other libraries like Pytorch. And yeah, apart from that, like the minimum type series representation, like that whole function is created from scratch.
Okay, okay, thank you very much. Okay, so I will give you more time to ask a question, because we have only 4 presentations in this session, so we are we have some extra time. So if you want to ask another question, I will wait a couple of seconds. Any questions from the audience? Okay, if there is no more question, thank you very much for your presentation. It was very, very interesting. And now I will. I think it's time for the breakout rooms. So thank you very much for this session. And now you can continue your discussions and ask more questions to the authors in the breakout rooms dedicated for every topic of this session. If you want, you can join them just now. They should be open now. And please, authors, go to the specific breakout rooms to maybe answer the questions from the audience. And it will be, I don't know, 5 or maybe more minutes to manage this questions. So thank you very much for your attention, and see you later, and have a nice another sessions during this this very interesting conference.